Bam! Mr. Taru, in this lesson we are going to learn how to solve equations that have more than one absolute value function in them. Our three examples we're going to work through are all going to have two absolute value functions in them, but this technique works for even more than two. There could be 3 or 4 absolute value functions in the single equation, and this technique will still work, even though that'd be a lot of work to go through. So the absolute value equations, or graphs, have turning points that occur at values that make the expression inside the absolute values equal to 0. You can rewrite the absolute value expressions as a piecewise function. The absolute value of ax minus b, the sort of general version of this language that's on the right side of the board, has got sort of a linear function inside this absolute value expression, but you could have more complex expressions inside here. If we have ax minus b, well then it's going to be rewritten as ax minus b if x is greater than or equal to b over a. And you're going to replace the absolute value of ax minus b with a set of the opposite expression, negative parentheses ax minus b, if x is less than b over a. Well, this b over a idea is again coming from, they're the turning points, they're coming from taking the expression inside the absolute value equation or function and setting it equal to 0. And of course we're going to add by b and divide by a with this sort of general form again expression that we're going to get x is equal to b over a. This is the x value of the turning points. Okay, so what? Well, for any equation involving absolute values, there are at least one turning point value for the variable of the variable for each absolute value. In other words, again, you might have more than just a linear expression inside your absolute value function, so for each absolute value you may get more than one turning point. The n turning points are used to split the number line into n plus 1 intervals. So if you find that you have, two turning points, two answers or x values that take the expressions inside your absolute value functions and making them equal to 0, then those two turning points are going to cut your number line into 3 parts. Now within each of those 3 parts, or those n plus 1 intervals, well, within each interval, each absolute value in your equation can be replaced by the expression inside the absolute value, kind of like just drop the absolute value symbol, if what's inside that absolute value symbol is positive within that interval. If what's in that absolute value symbol is negative within this interval, then you're going to replace it with its opposite, or that set of negative parentheses wrapped around the expression inside your absolute value function. Now when you do that, you're going to get, well, an equation without any absolute value symbols in it. Each of those new equations are going to be solved, and when you do so, you're going to be restricting your solutions to the corresponding interval that you use to create that new equation. And if you have a graphing calculator or some way to graph these functions that you're trying to solve, these equations that you're trying to solve, it would be really nice to be able to graph that and actually check your solutions with a graphing utility or a computer if possible. And when you're done, you're done. Yo, bam! And get to that first example. No. First example, 7 over absolute value of 2x minus 3 is equal to 2 over the absolute value of 3x plus 5. Okay, we're going to get these variables out of the denominator by cross multiplying because there's just one fraction on each side. And we have 7 times the absolute value of 3x plus 5 is equal to 2 times the absolute value of 2x minus 3. And now we need to figure out a way of rewriting this equation, whether it's 2 or 3 of these, without these absolute value symbols, so we can continue. That means setting the expressions inside these absolute value symbols equal to 0. So we have 3x plus 5 is equal to 0. Moving the 5 over, we get 3x is equal to negative 5, and dividing by 3, we get negative 5/3, which is going to be approximately negative 1.67, or negative 1.6 repeating. And here we have 2x minus 3 is equal to 0. Moving the 3 over with addition, we get 2x is equal to 3, and dividing by 2, we get x is equal to 3 over 2. So we have a number line that that's going to be broken up into three intervals by this turning point of -5/3 and this turning point of 3/2. So I guess maybe we could do this in color coding. Let's work with this first interval. Now again, that's approximately -1.6 repeating. So let's think about what if we were looking at an x value of -2. Well, an x value of -2, 2 times -2 is -4. -4 minus 3 is -7. So this first inequality is going to be, well, that inequality is going to be negative. I really want to be looking here. But that inequality is going to be negative. And 3 times -2 is -6, and -6 plus 5 is -1. So when we're to the left on the number line, when we're to the left of -5/3, both of our absolute value expressions are going to be negative. So they both need to be replaced with the opposite of that. So for this, let's call this interval 1, we're going to be looking at -7 times 3x plus 5 is equal to -2 times 2x minus 3. Now we're going to distribute these values of -7 and -2 through the parentheses, and we get -21x minus 35 is equal to -4x plus 6. Let's go ahead and move the -4 to the left with addition. We're going to add 4x to both sides. That's going to give us -17x minus 35 is equal to 6. Add 35 to both sides, and we get -17x is equal to 41. Let me just make sure that I'm heading in the right direction here. Yes. Okay, now we're going to divide both sides by -17 and get our first solution, which is x is equal to -41/17. Well, actually, I just misspoke a little bit. I don't really know if that's my solution yet. This is a solution to this equation that I rewrote from this equation with the absolute value symbols, set up for the interval to the left of -5/3. So this is only a solution if this is within this restricted domain, if you will. And -41/7, well, let's see here. 2 times 17 is going to be 34. And 34 is less than 41. So this is to the left. This is less than -5/3. Indeed, it's actually less than -2. So this is within this restriction or this interval in our number line, and so that is one of our solutions. Okay, now let's pick a different color here. Let's do blue for interval 2. Let's see, well, what's going to be the easiest number to work with to kind of test the signs between a negative number and a positive number? Well, that's going to be 0. Okay, well, 3 times 0 is 0, plus 5 is a positive number. And 2 times 0 is 0, and 0 minus 3 is a negative number. So for the second interval, this is going to be, these absolute value symbols are just going to get dropped and replaced with parentheses, and this set with a, the opposite of. So we're going to have, for interval 2, we're going to have positive, right? So 7 parentheses 3x plus 5 is equal to -2 parentheses 2x minus 3. And again, that negative, I want to bring in a opposite type operation into this parentheses because in the second interval this was negative, right? Okay. Again, distributing through the parentheses, we get 21x plus 35 is equal to -4 plus, x plus 6. Okay. Now we're going to move this 4 over to the other side with addition, and get 25x minus, plus 35 is equal to 6. I'm getting excited about being close to the answer, and I don't want to make a careless mistake. Now I'm going to move the 35 over with subtraction, and get 25x is equal to negative 29. Because this is a larger absolute value, so 35 minus 6 is 29, and it's negative, of course. And dividing by 25, we get x is equal to negative 29 over 25. And that, let's see, is that one of the solutions? Is that between 1.5 and is it greater than negative 1.67? Well, this is, did I write an approximation of this? Yeah, this is approximately equal to negative 1.16. So it certainly, our solution certainly does fall within the restriction of this interval. So this is a solution as well. Now, I'm running out of space here. So let's clear off our picture-in-picture. Very high tech here. Actually, that's the way I like it. Voila! Okay, our third interval, and let's go ahead and do this in white. All right, this is 1.5, so let's think about the value of 2. Get the glare off of there. 3 times 2 is 6, and 6 plus 5 is going to be a positive answer. And 2 times 2 is 4, minus 1 is also positive. Now this is going to come out to be, well, both of these absolute values are positive in this interval, so we just drop the absolute value symbols and replace them with a set of parentheses if we need to distribute like we do here with the 7 and the 2. Now, you don't want to notice a sort of a shortcut pattern in these problems. You want to create an equation, a new equation from each of these intervals, solve it, and then test those solutions against each of these intervals to make sure it falls within there. Now, with this one, you know, if you look at what we did with the first interval, both of those both of those absolute value symbols need to be sort of rewritten with an opposite type expression. Now, if I divide both sides of this equation by negative 1, I'm going to get positive 7 parentheses 3x plus 5 equals positive 2 times 2x minus 3. So the solution to this is going to be the same as what we've already found, and that was negative 41 over 17. Don't expect to necessarily get an exact answer again as you go through these multiple intervals that you're creating new equations from on your number line, but that does happen to be the case here. Now, I kind of want to say, you know, that this solution for this equation would have to be rejected because that solution for this equation, well, this equation was created using this rightmost interval, or as I labeled here with interval 3, and it doesn't fall. Negative 41 over 7, of course, is not greater than 3 halves or 1 1/2 or 1.5. So for this equation, this solution is getting rejected, but we've already seen that that was a solution for this equation from another interval. So I'm kind of throwing out an answer that I'm using, but again, don't expect that kind of pattern to show up on a regular basis. And that is the end of our first example. Next! Bam! No. Example 2. X is equal to the absolute value of 2x minus 4 over 5x minus 1. Okay, well, for this one, we can rewrite this so we can give the numerator and denominator their own separate absolute value functions. So we have x is equal to the absolute value of 2x minus 4 over the absolute value of 5x minus 1. Now we have this variable in the denominator, so we're going to multiply both sides of the equation by 5x, the absolute value of 5x minus 1, and we get x times 5x minus 1 is equal to the absolute value of 2x minus 4. Now this problem is a little bit different than the previous example because we have a value, the variable of x outside of the absolute value symbols. But the process that you go through to finish this problem is exactly like the previous one. It's not any different because there's an x out there. We're going to set each of these inside expressions equal to 0, find our turning points, get those on the number line, get it separated, and set up these equations. So because this is so similar to the previous example, I'm going to release the solutions one step at a time, and give you an opportunity to pause the video and try this one on your own before you see the solution. No. I fibbed a little bit. Let me help you finish this up. I'm not sure if you need this help or not. I don't know if you're watching this as an Algebra 1 or Algebra 2 student, and you might need to get a little hint on this, or if you're really advanced in mathematics and this is maybe hopefully not a waste of your time. But you have a quadratic. Now when you have a second degree and a first degree variable, you're not going to just get x alone. You need to set that thing equal to 0. And if I take the 5 times 4 and get 20, there's not a pair of factors of positive 20 that add to be the middle term of negative 3. So you need to finish this up with the quadratic formula. And that means that we're going to have an a value of 5, a b value of negative 3, and a c value of 4. So we get x is equal to the opposite of b plus or minus the square root of b squared minus 4ac all over 2a. Well, b is negative 3, so we're going to have the opposite of negative 3 plus or minus b squared minus 4ac all over 2a. Okay, well, you can see what's going to happen in here, I hope. Negative 3 squared is going to be positive 9. But you're going to have 9 minus, well, because this is a negative times 2 positive, so 4 times 5 is 20, and 20 times 5 is 100. Or, excuse me, yeah, did I say that right? 20 times 5 is 100. Well, 9 minus 100, if you're only accepting real answers, you're going to be taking the square root of a negative number, so there's not a real solution. There'll be a couple imaginary solutions, but not a real solution. So as far as real solutions, this would have, well, no solution. So we did not get a solution on this number line, a real solution that is less than 1/5. So from this equation, we're not going to get a solution to this equation. So now let's move on to the second interval on our number line. Now at this point, we got 5x plus 5x squared plus x minus 4, and 5 times negative 4 is equal to negative 20. Now there are factors of negative 20 that add to the middle term of positive 1. And, well, I ended up with that pair. I mean, we could talk about negative 1 and 20, 1 and negative 20, 2 and negative 10, 10 and negative 2. But you can take, with quadratics, the first and last number, the leading coefficient and the constant, multiply them together. And if that product has a set of factors, again, that add to the middle number, then you can use those factors to rewrite this into two, rewrite the middle term into two separate ones, or basically writing this in 4 terms instead of 3. So we're going to have 5x squared plus 5x. Actually, I want to put the, it doesn't matter what order you do this in, but when you're factoring like this, there's a little bit of thing I want to point out here. So I'm going to put the negative 4 first. Again, it doesn't really matter, but I just want to point something out here. If I put the -4 first, you're now going to, we've rewritten again that middle term with these two factors, and we've got 4 terms. You're going to factor this by grouping. What comes out of the first 2 terms? Well, they both have a common factor of x. Now, when you factor by grouping, you can factor by grouping if you can take something out of the first 2 terms and something out of the last 2 terms and get a new line that has in itself 2 terms which are like or are equal. So that means that I have to show that I've factored something out of the first 2 terms and something out of the last 2 terms. Well, this is 5x minus 4, and on the end of our equation we have a match already, 5x minus 4. Well, if this is already a match, then I need to show that I'm factoring out a positive 1. I need to show that I'm factoring something out, but I don't want to change these 2 terms. Okay, now we have x times 5x minus 4 plus 5x minus 4 plus 1 times 5x minus 4. And now these 2 terms have a common factor of 5x minus 4, so we pull that out. Set each one of these equal to 0. And we get x is equal to -1. Add the 4 to both sides, divide by 5, and we get x is equal to 4/5. Well, -1, we created this equation using this interval of the number line, and -1 is not between 1/5 and +2. So while this is a solution to this equation, it doesn't meet the restrictions of this interval, so we need to toss it. And right now we're looking at a solution so far for this absolute value equation of, well, of 4/5. So let's get on to the third interval and see what happens there. Alrighty then, we're getting right back to where we were in the first place with the first interval and ended up with a quadratic that is not going to have a solution. So, moving on to our third and last example. Last example. Absolute value of 2x plus 3 minus absolute value of x plus 4 is equal to 2. Looks a little bit different. Absolute values are on the same side. They're subtracted together, a little bit different than the previous ones, but they, again, all work through the same process. Now, as you set up these little equations, they're all going to be linear functions and much simpler to solve than the previous example. So I'm going to step out, again, release the solution one step at a time, and when we're done with this, don't tune out yet, we're going to replace this equal sign with an inequality and just see what that does, what that adds to our work at the end of the problem. So we found our turning points. We marked those along the x-axis. We tested the values of -5, -3, and 0, and realized that our 2 absolute values would be negative here, then negative positive, and then positive when we get to the right of 3/2. And that set up our following equations, which you, well, hopefully followed the process of solving those, like again, at least for the first group here, let's replace this absolute value with a set of negative parentheses, and then there's a minus from right there, And then we're going to replace the second set of absolute values with another set of negative parentheses, and they cancel out here, and we distributed this negative. We combine like terms. Negative 2 plus 1 is negative 1x. We combine the negative 3 plus 4, which is positive 1, and continue to solve for x. And we got x is equal to negative 1. Negative 1 was not in this interval of the number line, or not less than negative 4, so for this equation that was not acceptable as a solution. And then we repeated the process for the second and the third case, where we had a negative, positive, and then two positives. That gave us two final answers of x equals negative 3 and x equals 3 for this equation, which of course has our two absolute value functions in it, or expressions, or whatever you want to call it. Now, what if that was not equal to 2, but less than 2? So breaking out our very high-tech picture-in-picture here, we get this idea that, okay, well, we solved the equation. Now let's deal with it if it were an inequality. Well, those answers of negative 3 and positive 3 become yet another couple of critical values to separate our number line again. Now I have open dots on the negative 3 and positive 3 because the way I have this equation written, or this inequality written now, I want it to be less than 2, not equal to 2. If it was equal to 2, then these dots would be filled in. And I've picked a numerical value, an x value, within each of these three intervals on the number line, and we're simply going to plug them into the inequality and see if we get an answer that's less than 2. And if it is, then that portion of the inequality is part of the solution set. So if I plug negative 4 into here, I'm going to have 2 times negative 4, which is negative 8. And negative 8 plus 3 is a negative 5. And the absolute value of negative 5 is positive 5. And again, if I plug in negative 4 into this absolute value, negative 4 plus 4 is 0. The absolute value of 0 is 0, so we have minus 0. So we have 5 from this absolute value function minus 0. Is that less than 2? Is 5 less than 2? Well, we know the answer to that. The answer is a big fat no. So this portion of our number line does not work, does not give us a left side which is less than 2. Let's plug in 0. Well, when you plug in 0, 2 times 0 is 0. 0 plus 3 is 3. And the absolute value of 3 is, of course, equal to 3. Minus 0 plus 4 is 4. And the absolute value of 4 is positive 4, but I'm going to write minus 4 because of the negative that's in front of the absolute value symbol. I'm holding the board so it doesn't bounce on the other blackboard here. And 3 minus 4 is equal to negative 1, and indeed, negative 1 is less than 2. So if one number within this interval between negative 3 and 3 gives me a value less than 2, then I know every value between negative 3 and 3 is going to give us a value which is less than 2. So this whole interval is our solution so far. Now I don't think that this last interval is going to work, but let's check it anyway. Plugging in 4, we have 2 times 4 is positive 8. Positive 8 plus 3 is equal to 11, and the absolute value of 11 is 11. Minus 4 plus 4 is equal to 8, and the absolute value of 8 is going to be equal to, well, 8. And so we have 11 minus 8. Is that, excuse me, less than 2? Well, no. 3 is not less than 2. So this part of the number line is not part of our solution to this inequality. And our final answer, if it was the absolute value of 2x plus 3 minus the absolute value of x plus 4 is less than 2, the answer to that inequality is going to be x has got to be greater than negative 3 and less than positive 3. Or if you're using interval notation, that means that your answers are going to be between negative 3 and positive 3. And that is the end of my last example, the end of my video. I'm Mr. Taru. Go do your homework.